completely unprotected on the rooftop. This is also probably a typical, community scientist kind of way to use it. Is just slap it right on the top of the car and just start driving around, right? So a lot of this work that we've been doing is the planning part for how do we do this testing. We've done a lot of computational fluid dynamics modeling, CFD, to model the particle trajectory simulations. To fit inside the car. So we've been able to fit a T640 in there. And we've configured them so they're reporting at the highest time resolution possible. So, even though like 10 or 6 or 1 second reporting it's not great if you're doing like a stationary study because you don't really have high confidence in that value. But for mobile testing, you want to have as high time resolution as possible because every second you've already traveled, another tens of meters or something. So it's also important that we want to have ultrafine particle counts. So we have a CPC on board as well. And then these are the gases that we were able to fit inside the vehicle. We would have loved to also fit a black carbon monitor inside. We would have loved to fit in, other reference monitors, but we're just so space and power constrained because everything is running off of some batteries. And you can only keep all these instruments running on batteries for maybe about 6 or 7 hours on a drive. We did a lot of, again, as I said, a lot of modeling and planning for this work. So the two things we did were our computational fluid dynamics, CFD modeling, which is to model the fluid flow or the gas flow around whatever we're trying to do on this car. And then also some particle trajectory simulations. So you use the results of the CFD, the gas flows, as an input to your particle trajectories, and they will move differently depending on their size and on the free flow, the free flow gas velocity. And I just want to let you know that there are free and open source software solutions to doing this. So for me to do this kind of modeling work, I didn't I looked for what was free because I think that is the most. If you can find a free solution to do this, you can pass on this information to resource constrained groups to let them also be able to know that they can take on this work as well. So, for example, there's FreeCAD, which is like SolidWorks. It's like a 3D, solids modeling software. So that's free. And then there's a CFD open foam workbench. It's like a package that you can install. And so your FreeCAD, this is your 3D geometry. That's your input to OpenFOAM. So OpenFOAM is a free and open source CFD modeling software. So it solves the Navier-Stokes equations to create your fluid flow solution. And then OpenFOAM, that is your input to ParaView, which is also free. And that lets you visualize the fluid flow solution and also allows you to export the fluid field solution to whatever script you write for your particle trajectory analysis. Whether you do it in R or Python or whatever, you can then feed the ParaView solution into R or Python to do your particle trajectory simulations. And then the results from that, you can use that to further refine your design of your car, or maybe the sampling probe, or maybe the box that you're putting sensors in. So these are just some examples of the CFD modeling around our Chevy Volt. That's our latest vehicle. And so it's kind of interesting to see the results of the fluid flow solution, around the vehicle that you're going to use. I think we have this notion that we can put a sensor just on the roof of the car directly and, it'll work. And that's all we need. But if you look at the fluid flow streamlines, if you look, very close to the car rooftop, you see the fluid flow streamlines are actually originating, from near the ground. So whatever air is like close to the rooftop, it came from somewhere around here. And if you put your sensor there, is it like, well, is that the air sample that you're really trying to measure? Or are you actually trying to get more of an ambient kind of measurement? So if you want air samples that originated from, somewhere higher, it would be good for you to try to mount your sensor as high as you can on your vehicle. Because if you can mount it, if you can mount your sensor 1 meter above the car, then already the samples that you're collecting are coming from, up here and not from down here. Next slide, please. Okay. Oh, okay, thank you. Okay, so there's also some, modeling and planning that went to the particle reference monitor sampling probe. So, we might have this kind of inclination. If you are fortunate to have a particle reference monitor in your vehicle, you might want to just like put a tube like stick a tube out the window to collect your reference monitor samples, right? But for any of us who are particle physicists or aerosol scientists, that's not really great practice because particles, depending on how big they are, they have inertia. So they have resistance to moving, changing their movement direction if the gas flow is also changing. So this is probably not an issue if you're just measuring like ultrafine particles, maybe even PM1, maybe PM2.5, the effect maybe not so bad. But if you're trying to also do mobile sampling of, larger fractions of particles like PM10, it really would be good to consider the inertial effects and how you sample the particles. And so perhaps a simple tube out the window would not be, would not be sufficient. Perhaps you want to consider doing some modeling for custom probes to let you get representative particle populations by the time it gets to your monitor. So here's an example. This is my design of a double shrouded probe. There's kind of I guess let me get some background. So for sampling of particles in a moving airstream, I think the most popular technique is to use an isokinetic probe, which is a sampling tube that has a small diameter inlet, and then the velocity at the inlet of that probe is supposed to be matched to the free stream velocity. So as long as the velocities of the air match the velocity that you're sucking air into the probe, you're going to get a representative population of particles. But if they don't match, you're going to bias your sample to either having too few or too many of the larger particles, and that will bias your overall picture of the particles. So isokinetic probes are great and fine. It's just that they have a pretty narrow window of what speed you can be moving at, plus or minus 10%, I guess, of what speed you're supposed to be moving at before your sample becomes very biased. When you're driving in a city, you have lots of stop and go traffic. You might be driving fast on the highway and then all of a sudden it's a traffic jam and so you're driving slow. So the isokinetic probe, I think, is not a great solution for mobile monitoring, but if that's what you can do, that's better than nothing, right? Another approach to doing mobile monitoring of particles is using shrouded probes. We typically see this on aircraft campaigns and aircraft measurements to get particle samples. And the idea of a shrouded probe is that you want to create a deceleration zone to slow down your sample flow. And when you slow down the entire sample, you give the larger particles more time to react to the changing gas flows. And so if you give them more time to react, by the time you get to your sampling probe inlet, you're more likely to have gotten a representative particle population. And so I think it was only until the last several years people have started going into the idea of a double shrouded probe. So you have one deceleration zone, and then you put a second deceleration zone before it. So you give the sample more time and more opportunities to decelerate and adjust their movements to the sample that would eventually go into your probe. And so this is a custom design, and there was CFD modeling that went into that. And then the results of this CFD modeling went into an R script that I developed to figure out what kind of sampling efficiency would we get of different size particles from like 0.1 to 10 microns at different speeds that we're driving the car. And sorry, these are miles per hour, not meters per hour. So we can see that if we drive at pretty high speeds, on the highways, for 10 micron particles, we're getting about a 30% oversampling with this double shrouded solution. And I would say that for this broad range of driving speeds, to have this kind of variability and bias for PM10, that's quite good and that's quite tight. If you were to try to do this with the isokinetic probe or just a regular tube, you would probably see oversampling efficiencies of hundreds of percent by the time you get to 10 micron particles. So this is some images of the modeling that was done for one of the testing scenarios, which is to put sensors in a very controlled flow duct. So this controlled flow duct, it's an HVAC duct. It's a 14-inch by 8-inch rectangular, HVAC duct, and we have some tapered sections and some 4-inch, HVAC ducts as well. And then you can see like 3 sensors we would put inside there. And so to make this a very controlled environment, a controlled flow environment, we had to do a lot of like funny things, like put an axial fan in the back that's always running, so that even if you're at a stop sign, you're still pulling flow through whether or not you're moving, right? There's also the flow coming in. And so when the flow comes in, it's going to come in as a jet. So, we designed this diffuser plate assembly, and with the CFD modeling in here, we were able to show that this is the minimum number of diffusing plates and angles that we would need to stick in here so that by the time we get to the test section, the flow has already been, well distributed. We're approaching, a more uniform flow distribution in the test section. And then we also figured out that we can stick in this automatic balancing dampener. This is just an off-the-shelf piece for HVAC stuff. So this is a spring. It's very hard. I know it's all dark, so you can't really see it, but it's like a flap, a spring-loaded flap. And so the faster you're driving, the more pressure is being placed on that flap from the wind. And so it'll start shutting itself more. So that slows down the flow coming in. So it's like a self kind of adjusting flow mechanism. So that's that. But this is not something we would expect for more community scientists to do. This might be more realistic, right? Having a box that you put your sensor in to shelter it from the wind and from the sun. So this is a design that I've been working on. Maybe our natural inclination is to have a box and have a hole in the front and a hole in the back and just let the air just shoot right through it, right? But I've done some modeling of that kind of idea, and there's kind of non-ideal conditions of the turbulence and the flows going through. So, I'm starting to go to this kind of solution where you have a hole in the front of the box and then a hole at the side of the box. So inlet and then on the side an outlet. And that's because I'm trying to capture, there's a low pressure area I'm trying to capture here to take advantage to dry flow in and dry flow out. And then when you do the CFD model, you can actually see that the gas streamlines are actually making this kind of circuitous pathway before they exit out the outlet. And so that's kind of nice because it lets you have a well-mixed kind of box for your sensors to sample from. It allows some amount of residence time in there. Yeah. And also because of this kind of, by the time, if you put sensors around here, it's not that turbulent. So that's also a nice, peaceful, calm location for the sensors. So yeah, going forward, this is something that I hope to get as a systematic effort. So we're still fabricating our final testing scenario. We are testing sensors in a more of a pilot kind of study. And we do have early indications of effects of mobile deployment of sensors. This is a graphic that I kind of snipped out of a paper that we put in ESNT. Sorry for the small font, but you can find it when you get the slides. So this kind of shows, when we test the purple air, the PA2, for their PM 2.5 signal against the T640, we look at the R squared. Thank you. So we have a scenario one. Back then we called the controlled flow duct our scenario one. And you can see pretty high R squareds as a function of walking and bicycle speeds, the speeds you would drive on local roads, the speeds you would drive on arterial roads, and then these are highway speeds. So even if we're driving pretty fast, you're not seeing. They put it in a box. These acronyms FTB and TTB, that's kind of outdated. That was based on a front to back flow design, and then TTB is a top to back. So we had a hole in the top of the box and a hole in the back. So we thought these different kind of configurations might impact it. So, if you put the sensors in the box, their R squared is still pretty, it's pretty good. And then also for the rooftop scenario, this is also kind of outdated, but we used to test the sensors in different orientations, right? So roof default means the purple air was installed this way, where the inlet is on the bottom. And then roof FF facing forward is if we angled the sensors to have their inlet facing in the direction of motion. And then FB facing backwards is if you angle it that way. I don't think we're going to do that anymore. I think we're just going to do the default, how the manufacturer says you should orient the sensor, just because we're getting into too many permutations of how to do this testing. And it's just too resource intensive. But you can see that when you start putting it, on the roof and in weird kinds of orientations, you're getting a lot of degradation in the R squared. And then we had the same kind of image, but for the normalized mean absolute error. So kind of the accuracy. So if you put it in a controlled flow duct and in a box, it's not terrible, the errors, but they do get progressively worse as you drive faster. And then by the time you start putting sensors just directly on the roof, unprotected, you can get pretty extreme errors, especially as you drive fast.